Welcome to this third Neuroergonomics webinar. So good morning, good afternoon, or good evening, depending on where you are. So we are very happy to welcome you on this webinar dedicated to neuroergonomics, obviously, and especially to neurotechnology and system neuroergonomics. So this is live on YouTube. So for information for us, the speakers, we are on a Zoom meeting separately. So we are kind of 30 seconds ahead of you. So don't worry if you feel some delay, and later don't hesitate to ask a question as soon as the question comes, so you don't wait for 30 seconds for the answers. So as you will see, we are also automatically captioned. So you see this text on the bottom, so that's for making the speech accessible to everyone. It's not perfect. I guess with my heavy French accent, probably is going to miss some of the stuff I'm saying, but seems not too bad. Well, I did not introduce myself. So I am Fabien Lotte. I'm a research director at INRIA in Bordeaux, working on brain-computer interface and their use for many applications, including neuroergonomics, obviously. And I'm hosting this seminar with this webinar with Stephen Fairclough. And so I guess without further ado, let's start the webinar. Please enjoy, and I'm giving the floor to Steve to give an introduction before we hear the speakers.
Thank you, Fabien. Good afternoon, everybody. Welcome to the webinar. My name is Stephen Fairclough. I'm a professor of psychophysiology at Liverpool John Moores University in the UK. And Fabien and I will be doing a short introduction to the webinar before we introduce the four speakers. So I'm going to get that underway now. So as Fabien has said, the topic of this third webinar in this series is neurotechnology and systems neuroergonomics. Most of you, I think, know this already, but for those of you who don't know, a journal called Frontiers in Neuroergonomics was launched last August, I think. And this webinar is one in a series in order to introduce the journal and the themes of the journal to everyone. So we have 7 speciality topics that have been put together by Hassan Ayaz, Frederick De Hayes, and Waldemir Kowalski, who were the field chief editors. And the field chief editors did a webinar to introduce the journal at the end of last year. Amory Brower did a webinar, organized a webinar of speakers to talk about consumer neuroergonomics in January. And this third one is our turn, is Fabien and I's turn to talk about the topic neurotechnology and systems neuroergonomics. And like this talk, this webinar, and like the other webinars are all available through the YouTube channel that you're watching this presentation through. So the general theme of neuroergonomics, of course, is looking at how the brain works and measuring brain activity in real world settings. So for our particular speciality topic, there is an emphasis on looking at how neurotechnology may work in the wild. So looking at how neural interfaces would work in various real world operations, whether that's transportation or other things, and looking at other applications in everyday life, looking at neural interfaces and neural technology in the context of leisure, of health, as well as everyday work. And of course, once you start to introduce this sort of emerging technology into the real world, you end up with a technological system that is interacting with other existing systems. So this could be organizational principles in the workplace. It could be some kind of economic policy. It could be some kind of health policy. So we're very much interested in how we develop these neurotechnologies and how we place these neurotechnologies in the real world and how they interact with existing systems. Now, as part of the kickoff for this particular speciality topic, Fabien and myself were asked, and the other speciality editors have also been asked to write grand challenges papers to set out what we thought were the biggest challenges facing the research in this particular topic. So for this particular webinar today, we're going to focus principally on our what we call our first 2 grand challenges. Coming up with robust and reliable neurotechnology and designing user experience and evaluating systems. The system perspective stuff I already alluded to in the last slide. So what I'm going to do now is hand the floor over to Fabien, and Fabien will talk about robust and reliable neurotechnologies. Over to you, Fabien.
Thank you, Steve. So as Steve mentioned, indeed, one of the grand challenges that we need to solve to be able to use neurotechnology in the wild is to make them robust and reliable, because so far, for the moment, neurotechnology are not reliable in the wild. And actually, as you can see on that slide, I put the in the wild into brackets, because if we are really honest with ourselves, neurotechnologies are not reliable, full stop. So we really need to make them more reliable. So they are not reliable for many reasons. One of them is that obviously they have usually low accuracy in decoding the user's mental states. For instance, if you want to use a brain-computer interface to decode left hand versus right hand imaging movement, or to decode a low level of workload versus a high level of workload, typically these systems have an accuracy around 70 to 80% on average, which is good, but not that great. Obviously, for some users, the accuracy can be very high. That you can see, for instance, on that picture. Some user can go near 100% of accuracy, but some other can also be near 50%, which is a chance level in that case for two conditions. And in these examples, which is a BCI based on imaging movements with two imaging movements, you can see that roughly half of the users are below 75% of accuracy. So obviously, there's a lot of room for improvement. And that was in the lab. So obviously, that would have been most probably even worse in the wild. Next, please. Another challenge and another problem is that when we design neurotechnologies, we are using neurophysiological signals and sensors that are very sensitive to noise and artifacts. For instance, they are sensitive to muscle movements for EEG signals, to eye movements, etc. When you move, when you frown, etc., etc. You can see that on the picture. That's in the lab already. And if you move in the wild, outside the lab, there are even worse problems with, for instance, motion artifacts when the user are moving around, moving their head, walking. There are also electromagnetic artifacts if you are using neurotechnology, for instance, in plane cockpits or in cars, etc., etc. So obviously, these types of noise and artifact degrades the signals and make the neurotechnology even less reliable. Next. And finally, as if things were not already quite bad, these neurophysiological signals, they are very non-stationary. So as I mentioned, they already change a lot between users, but even for the same user, they change over time. They change across days and even within days. So for instance, on the picture that you can see on the bottom right, you can see 2D projections of EEG signals across days. So here, each color is a different day. And each point is EEG signals while the user was imagining given mental imagery tasks. So here you have, I think, 7 different colors at 7 different days. And the user were doing the same thing in all these days, imagining the same task. And you can see that these points, they are all over the place. The different colors do not overlap at all. So meaning that EEG signals change a lot across days, even for the same user who is doing the same task in all these days. So obviously that makes building neurotechnologies on these signals a challenge. Next. So what can we do to design robust neurotechnologies? So I think there are a number of sub-challenges that we can tackle to try to make that better. One of them is to be able to deal with this noise, artifacts, and non-stationarities. And I think that to do so, what we need to do as a community is to try to understand better, to have a deep understanding and to design models, both conceptual and computational models of the noise and non-stationarities. Can we, for instance, model the noise, the artifacts, to make sure to understand their signature, for instance, their temporal, spatial, or spectral signature, and how they affect, for instance, EEG or other neurophysiological signals? Something for non-stationarities. Can we model how these non-stationarities affect neurophysiological signals? Can we model when do they affect these signals and how they do so? If we can have some models to do that, then we can hopefully tackle them in an optimal way. Next. For instance, from these models, from these models and understanding, we can design new hardware and new software that are based on these models to tackle them in an optimal way. For instance, we could design new sensors that can record neurophysiological signals with high signal-to-noise ratio, and they can be better because they know what type of noise they are facing. Similarly, we can design new denoising algorithms that can specifically target the known signatures of the noise and artifacts and know when to remove these artifacts in an optimal way. Similarly, if we have models of non-stationarities, we can design, for instance, neural signal features and decoders that are invariant to these non-stationarities. We can, for instance, design decoders that will be orthogonal to the sources of non-stationarity so that they are stable at all time. Alternatively, we can design adaptive neural signal decoders that will track these non-stationarities and adapt the parameters of the decoder accordingly, depending on when there are non-stationarities or how they affect the decoding. And finally, we need to be able to do all that, all these algorithms, denoising, decoders, neural signal features, hopefully online. For many neuroergonomics applications, we need to use these neurotechnologies online. And so we need to make sure we can do that in real time and calibrate this algorithm ideally on the spot. Next. Another way that we can hopefully design robust neurotechnologies would be by designing effective and efficient decoders. Because as I mentioned, we need high accuracy neurophysiological signals decoder. And we need them to be easy and fast to use. So one way of doing that is, for instance, by exploring deeper multimodal decoders. That is, decoders that use not only a single source of brain signals, for instance, but multiple types of brain signals, multiple types of neurophysiological signals, for instance, EEG together with FNIRS or EEG with EDA, ECG, other inputs like eye tracking or classical inputs like keyboard and mice. And so we need to design algorithms that can fuse this information efficiently and effectively. Next. If we want to use this neurotechnology in the wild and have decoders that are easy and fast to use, we also need to make sure that they have a calibration time that is as small as possible, and ideally no calibration time. Because in the real life, we don't have the time, we cannot afford to ask our users to collect hundreds or thousands of data from each user before they can use the system. Ideally, they need to use the system as immediately as possible. So we need to reduce the calibration time, and that means we need to calibrate and train our models on as little data as possible. So for instance, to do that, we need to explore artificial data generation, for instance, building artificial brain signals that can complement existing real brain signals from the user to build large databases from only a few signals from a target new user. So we can calibrate the system quickly enough. Or we could explore better transfer learning algorithms that can be calibrated on data from past users and can be tweaked with only a few examples from a new user so that the system, the neurotechnology, can be used as fast as possible. Next. If we want effective and efficient decoders, we also need to have specific and robust biomarkers, meaning that we need to have neural signatures that are really specific to a specific mental states, for instance, workload, and that change only due to that mental state and not due to other mental states. For instance, we want something that is specific to workload, but does not change due to fatigue or engagement, for instance. And for that, we need improvement and new research in psychology and neuroscience. In psychology, we need probably better definition of the mental states and the mental constructs that we are working with to make sure that their definition is specific and does not overlap with other definitions. And we need neuroscience to precisely characterize the biomarkers that reflect these mental states and constructs. Next. And finally, to do all that, to solve all these challenges, both to deal with noise, artifacts, non-stationarities, and design effective and efficient decoders, we obviously need data. And we need large-scale data, meaning a lot of data, and we need real-life data, not lab data. So ideally, we need data that have been recorded across many contexts, across many applications, across many days, across many users, so we can really capture the variability that is typically present in real-life situation in the wild. If we can have these large databases, build these databases and share them with the community, we'll be able to design much better algorithms and therefore hopefully much more robust neurotechnologies. Steve, I'll let you present the next grand challenge.
Thank you, Fabien. So I will be talking about the second grand challenge in our paper, which is to do with user experience and how we evaluate these systems. In recent years, I've been thinking about this more and more about all kinds of different neurotechnologies and asking myself the question, if these systems exist, how will they improve the quality of human-computer interaction in the general sense? What values and what utilities will they offer to the user? Now, so I did some looking around in the literature and I came up with this table. And the first thing in this table posits a number of criteria, all of which will enhance the quality of, are necessary to enhance the quality of human-computer interaction across a range of applications of neurotechnology. So first of all, we have a series of a category of neurotechnology which is able to detect context and to proactively adapt software. You're going to be hearing about some of those later on from the speakers. So context awareness is one enhancement that can be offered from neurotechnologies. We would hope that if the system is able to proactively adapt in the right sort of way, then it will improve the ability of the person to focus on the task. And it will also allow the user to remain calm and not to feel overwhelmed by information. So it's quite a lot of applications in the area of workload and overload and so on, which are dedicated to that. And if those things are happening, then we would also hope that the performance of the user is improved when they use this kind of technology. Now, one thing that does happen, because we take signals from the brain and the body, and these signals interact with classification engines and can adapt with software adaptation or AI or whatever, then there is a certain level of invisibility to this sort of interaction. It can occur outside the awareness of the user completely or in the periphery of the awareness of the user. So these are all things that potentially the system offers to the user. Now, if the system is working well and has been designed correctly, then we would hope that if people use the system repeatedly over a period of time, that those benefits, do not disappear after the first couple of seconds. And with familiarity, the benefits are continued and are sustained. So we don't have just a novelty effect of using a BCI or using something else. We have something that is a tool that can be used for a long period of time. Fabien has already referred to this, but obviously we need our systems to be robust and to be able to function reliably across a full range of their operating conditions. So a lot of the stuff that Fabien was talking about treating the signal is absolutely fundamental to creating robust neurotechnologies. And we would hope that if the system's been designed correctly so that the adaptations are useful and offer utility to the user and that they work in the way that we expect, then the user will trust the system and will perceive that neurotechnology is supporting them in what they want to do. And that is what makes a system desirable and enjoyable and satisfying to use. Now, obviously, we're probably not going to talk about this much today, but we have to mention it at least, is that when we're taking data from the brain and the body, that is quantitative, that is kind of high fidelity, and that really reflects unconscious as well as conscious psychological processes. There are issues around data privacy. So users want systems where they are able to handle and store and understand how their personal data is being used. And we've also seen papers in recent times about the potential for hacking with this sort of technology. So as a corollary of that, we want systems that are secure and where the sort of personal data that comes from the brain and the body is protected from unauthorized access and any kind of malicious attacks. Now, the second part of the interface design that I would like to talk about is basically how we achieve some of these things that I've talked about in the last table. It kind of goes without saying, really, that we need our sensors to be comfortable and to be unobtrusive, to go comfortable for long-term use, and unobtrusive in the sense that they don't interfere with the person's ability to move comfortably around or to operate in the office. And also they're unobtrusive in the sense that they don't make people feel self-conscious if people are using these technologies in public spaces. A large part of the benefits that the systems offer are to do with the ability to adapt user interfaces and do the adaptations in real time. Now, these adaptations can take various forms, and we already, have a kind of taxonomy that Thorsten Zander put forward, where we have active neurotechnologies, where a person has to think about something in order to achieve a command. We have these passive systems that just basically take data from the brain and the body as it occurs spontaneously. And we also have reactive mechanisms for interface control, where the person is presented with a stimuli, and then the response to that stimuli is a thing that is registered by the system. The P300 speller from BCI being the most common example of that. Now, a lot of research in this area focuses quite correctly on classification accuracy, on how well the combination of different measures are able to classify one psychological state from another. But if I could just direct your attention to that bar chart on your right-hand side of the slide, this is a bar chart from a piece of work conducted by myself and Alexander Karen and Carl G. Lead about 6 years ago that we published at CHI. And what you're looking at there is this is a system that's taking signals from EEG and from psychophysiology to make a binary detection of whether someone is interested or not. The blue columns that you can see is the F1, is the classification accuracy as defined mathematically. But we also asked people what they thought the accuracy of the system was. And the green bars that you can see are the subjective accuracy. So you can see subjective accuracy lagged a little bit behind mathematical accuracy. So this is what I mean by understanding user perceptions of how the system is operating and how accurate the user perceives the system to be. A lot of the neurotechnologies that we use kind of, I guess, are spawned in a way from kind of neurofeedback sort of ideas, where people are having to actively self-regulate their own neural signals. So I think we need to understand more about feedback with these sorts of technologies and understand more about self-regulation as it occurs in the context of the self-regulation of neural signals. And for when I see neurotechnologies mentioned, they're automatically presented as totally autonomous systems. So if the brain detects this thing, then this thing happens automatically. But if you look at the human factors literature, and particularly the influential paper published by Parasuraman et al. In 2000, you can see that there are many levels of automation that we can use. We can have partial automation. We can ask for confirmation from the user. So we can do lots of different things to make our interface design smarter and less autonomous and draconian for the person. So these are things that I think we need to think about. And finally, because I am aware of time, that we need to get on to the speakers, is that when we evaluate our neurotechnology, it's really important that we show in an evaluation methodology that the neurotechnology offers some of the benefits I referred to in the last slide. But evaluating a technology that doesn't exist yet can be challenging from a methodological point of view. So if you built a neurotechnology and you want to establish how well it works, what do you compare it to? So people have looked at all kinds of different things there. People looked at random systems. People have looked at systems that runs off yoke systems, that there are systems that run off data that have been recorded from another participant. People have looked at systems that run according to different sort of triggering criteria. But I think we need to understand more about evaluation methodology and how we're going to actually evaluate these sorts of systems. So that is Fabien and I's introductory comments to this. So we're really, really pleased to be able to introduce an excellent lineup of speakers. And we're going to introduce each one in turn. And just to point out here that really what we're going to be looking at today is there's quite a large emphasis on the so-called passive brain-computer interface approach, looking at implicit interaction, looking at cognitive probing methodologies in order to create these adaptive systems. But obviously, when you move from the unit of a person operating with a system, the next scaling up really is looking at groups of people interacting together. So we're also pleased to include a talk about synchronization and hyperscanning, so we can look at that kind of application as well.